Welcome to this guide about using a utility function to represent personal or enterprise risk policy. In the recommended form, a simple scaling factor, the risk tolerance coefficient, is sufficient to define a logical, consistent risk policy. The Utility Elicitation Program, UEP, is designed to capture one's risk attitude in this single parameter. I'm John Schuyler, a decision analysis consultant and trainer. I developed UEP to help clients and course participants determine their risk policies. UEP is now a web application that one accesses through an internet browser. The program is available free, except to competitors. The new improved UEP is a key supplement to my course materials and books. I am offering UEP as a way to teach and promote a simple and elegant approach to risk policy. If you are already familiar with utility functions, you may want to proceed directly to the portal page that has a link to UEP. The URL is repeated at the video end. If you prefer full detail up front, you may want to choose among video and written materials at the same web page. Or continue with this video for a quick overview of decision analysis, risk policy as a utility function, and an introduction to UEP. Perhaps nothing is as important to personal and business success than making good decisions. Decision analysis, DA, is the discipline for analyzing decisions under uncertainty. Decision analysis uses probabilities to capture judgments about risks and uncertainties. First use of probabilities in the foundation expected value calculation began in 1654. Expected value, EV, is simply a probability-weighted average of possible outcomes. Measuring outcome quality or value is at the heart of decision-making. This is decision policy. Decision policy is commonly separated into three elements: objective or objectives, and how quality or progress toward the objective is measured; time preference, which is most often time value of money; and, if necessary, risk attitude, expressed as risk policy. Let's take a look at a popular business decision policy. Many businesses state that maximizing shareholder value is the most common objective. For discussion, let's assume we measure project outcome value in US dollars. Time value of money is recognized in the usual net present value equation. And risk attitude is important if the company is conservative in its decision making. Let's assume a company is risk neutral. Expected monetary value, EMV, is the probability weighted NPV equals expected value NPV. EMV is also called mean NPV. The EMV decision policy is choose the alternative with the highest EMV. This applies best when the objective is to maximize the EMV of the company. Let's summarize the DA process. The decision maker has a way to measure outcome quality, such as NPV. Probabilities capture expert judgments about uncertainty. These are combined in the expected value calculation. The decision rule is to choose the alternative with the highest expected value. The prominent EV calculation tools are decision trees and Monte Carlo simulation. Each tool calculates expected values, though in very different ways. Trees and simulation both have advantages. Often, both methods are used for different parts of the same analysis. Let's take a quick look at a simple decision tree model of a capital investment decision. The decision is to approve or drop a project. For simplicity, we have only two possible outcomes: success or failure. Success, NPV, is worth $10 million, net of investment cost and taxes. Failure, NPV, is minus $5 million, losing the investment cost after effective taxes. A subject matter expert judges the probability of success, PS, at 60%. The bottom branch is a drop or do-nothing case for comparison and has 0 value. Decision trees are solved working right to left. The possible outcome values are the NPVs at the right. The outcome chance node's value is its EMV. Here is the EMV equation. EMV is the sum of the outcome probabilities times their NPVs. EMV equals 0.6 times 10 million plus 0.4 times minus 5 million equals 4 million. This is placed on the branch leading into the node. $4 million is the value of the node and the branch leading into it. Comparing alternatives, $4 million EMV is better than 0, so the better choice for the EMV decision maker is to approve the investment. Inferior choices are pruned as indicated by the cut marks. Thus summarizing, this investment opportunity is worth $4 million to a risk-neutral decision maker. Note that the actual outcome will be either plus 10 or minus 5 million. However, over a long run, many investments like this will add $4 million NPV on average to the company. This decision tree assumes the EMV decision policy, which represents a neutral risk attitude. Would you approve this risky investment? Often management books will say only, it depends on the company's risk tolerance, risk aversion, risk appetite, or something similar. That's not very helpful, is it? I ask my classes whether anyone knows his or her company's risk policy. Some will respond with one or several metrics or hurdles. None of these is adequate, individually or in combination. Risk policy is to guide in making risk versus value trade-offs. Consider 2 alternatives with uncertain outcomes represented by these distributions. Here we have the classic dilemma. A, the narrow distribution, has much less uncertainty than B. B has higher expected value, but more uncertainty or risk. Scale matters, and let's assume that the lower possible outcomes for B would cause serious damage to your or your company's net worth. Which would you choose? If you are risk neutral, the widths of the distributions don't matter, only their EMVs. Calculating the probability weighted average is straightforward. Since these curves are symmetric, the EMVs are in the distribution centers. EMV is an objective measure of value under uncertainty. However, for the risk-averse decision maker, each alternative is worth less than its EMV. The cash-in-hand value is called the certain equivalent. Where are we going with this? Using a utility function to represent risk policy provides a way to calculate certain equivalents. Think of a certain equivalent as a risk attitude adjusted EMV. Decision makers often override the EMV decision rule in important risky decisions. This is rational and often done using experience and intuition. A more consistent approach is to have and apply a risk policy expressed as a utility function. This idea is not new. Daniel Bernoulli first proposed a utility function in 1738, and the concept is now well established in economics. Here are 3 characterizations of risk attitude as utility functions. On the charts, the x-axis represents the objective value measure, NPV. The y-axis represents how the decision maker feels about the outcome. This video and the Utility Elicitation Program assume that you are a conservative decision maker and that you want to be consistent in making value versus risk trade-offs. Using a utility function for risk policy provides that consistency. Look at the right utility function. You may recall the law of diminishing marginal utility from school or college. As you get more and more of a good outcome, additional units are progressively worth less. People hate losses, and at the left side, the negative utility is getting steeper as loss worsens. Most decision analysts advocate using an exponential utility function, so-called because of an exponential term in the simple equation. The 45-degree line represents risk neutrality, an EMV decision maker with infinite risk tolerance. The curvature is defined by a single parameter, a risk tolerance coefficient. Its symbol is lowercase r. I call the y-axis risk neutral dollars. It's not real money. However, 100,000 risk neutral dollars feels 100,000 times better than $1. R is just a scaling factor. Higher net worth people tend to be more risk tolerant and would assign a higher value to their risk tolerance coefficients. Conceptually, Warren Buffett and I have the same utility function shapes. We just have different scales. Mr. Buffett has more zeros on the X and Y axes. Back to John's, Mr. Buffett's, John's, Mr. Buffett's. So the scales are identical in shape, it's just a matter of the numeric scale on the axes. There are many possible utility function shapes. Most practitioners settle on the exponential shape because of its very desirable properties. I recommend this formula so that the units are more meaningful, risk-neutral dollars. Note that R appears in the equation twice. If you accept the exponential shape, then all we need for your risk policy is to determine R. This is how the expression might be expressed in Microsoft Excel. I've used RTC as a symbol for R because Excel reserves R for special use. Don't be alarmed by that equation that converts outcome NPV into utility units. It is somewhat similar to the present value equation that converts a future net cash flow amount into a net present value equivalent today. The upper equation is the form that most analysts use and recommend. The lower equation is equivalent, but uses an exponential function instead. Using the utility function, we translate each outcome NPV into its utility value. Expected utility is the probability-weighted value of outcomes in utility units. The expected utility decision rule is to choose the alternative with the highest expected utility. By nature, we are all EU maximizers, though sometimes outcome quality depends upon multiple criteria and not just NPV. Multi-criteria decision-making is based on converting various outcome qualities into a composite utility value. To be more meaningful, I advise converting each alternative's EU into a certain equivalent. Certain equivalent, CE, is a measure in your real currency. We do the EU to CE conversion by using the utility function in reverse. Note that risk aversion should only affect decisions with large outcomes. For small, everyday decisions, such as buying an extended warranty on a toaster, we can be risk neutral. The CE is about the same as EMV. We only need to consider risk attitude in decisions where the outcomes are large and important. Let's step back for a moment. Decision analysis is founded on the concept of maximizing expected value. The decision rule is to choose the alternative with the highest expected value. In business, the dominant outcome metric is NPV. I advise bringing in non-monetary considerations as either NPV equivalents or embedded in cash flow projections as cash equivalents. If risk-averse, we transform the NPV amounts into utility units. Then either maximize EV utility, expected utility, EU, or equivalently, maximize certain equivalent, CE. The key to developing a risk policy is to determine the utility function. One way is to examine a record of past decisions and infer the utility function shape. This is problematic because of insufficient examples and inconsistency. If we assume the exponential utility function shape, this greatly simplifies the matter. More convenient is to consider new hypothetical decisions. Now we only need to capture the decision maker's R. Someone can present you with a series of hypothetical decisions and, from your responses, determine R values. The values will vary widely until the decision maker's intuition becomes calibrated through experience. This process is called elicitation. I developed a Utility Elicitation Program, UEP, to make the elicitation process easier. UEP's sole purpose is to help the decision maker determine his or her risk tolerance coefficient. It simulates decision-making situations much as we would do in an elicitation interview session. There are three parameters as we saw in the decision tree: PS, probability of success, NPV of success, and NPV of failure. A planned enhancement to UEP is an option to replace the two single-point NPVs with an NPV outcome distribution. There are three question types. PS type, you judge the minimum probability of success to accept or retain a risk. CE, you judge the certain equivalent of a risk. And share, you judge the optimal share you want of a large economic project. Questions may be worded in either project buy or sell perspectives. The generated questions are random but reasonably scaled to your maximum typical investment amount. Based on your answer, UEP calculates R. Next are examples of the three question types. Here we have a solved decision tree for an EMV decision maker. These outcome values are NPVs net of taxes. The EMV is positive, indicating that this is an economically attractive investment to a risk-neutral decision maker. The certain equivalent, CE, is the cash in hand value of this risk. CE is less than EMV for a risk-averse decision maker. What is the most you would be willing to pay to acquire this project? That amount is your certain equivalent. From your CE answer, UEP calculates R. Here I've scaled up this project. The amounts are in millions of US dollars. Assume $500 million is too much to risk on any project. What is your optimal share or ownership fraction of this project? From your share answer, UEP calculates R. Now we're back to the example we saw earlier, though here PS is not given. Suppose you are a small business owner and occasionally make risky investments in the neighborhood of $10 million. A new project comes your way. Success is worth $10 million and failure would cost $5 million. Your subject matter expert has not yet assessed the probability of success, PS. What is the minimum PS you would require to be just willing to approve this investment? From your PS answer, UEP calculates R. Unless you are very experienced at judging risk versus value trade-offs, expect that your R's will vary widely. But with practice and feedback, your R's should converge around some number. When you settle on an R, then that, plus the utility function shape, defines your risk policy. This chart shows computed R's for the PS type question we saw on the last slide. Back to our decision model, you may factor the units up for a large corporate decision or down for a personal decision. Consider your answer. Now, find your answer on the x-axis. Then go up the curve and read the y-axis value. Suppose you judge 50% is the minimum PS before you would approve this investment. The red dot shows this probability and the corresponding $10.4 million R. Setting up hypothetical decisions scaled to the decision maker is a bit of a chore. So over the years, I've developed versions of UEP to help with the elicitation process. The calculations UEP performs can be done or easily verified in Microsoft Excel. Here I have a spreadsheet set up for the PS question. These are millions of dollars in PV, and our EMV and certain equivalents will also be in millions of dollars. The utility column and the expected utility column are in risk neutral dollars, millions, and we'll convert back to real dollars, certain equivalent, once we have expected utility. Note the outcome values are the same as the problem we saw earlier, and we'll change the probability of success in a minute. The R cell can't be named R because of a restriction in Excel reserving the R as a symbol, so I'm calling this cell R tall. So here's a ridiculously large risk tolerance coefficient in millions of dollars. Let's look at some of the calculations. Here's our probabilities of success and failure, and the EMV is simply the sum of the products probabilities times the NPV outcomes, $7 million EMV. So it's a good project for a risk-neutral decision maker. Here's our utility column. These are equations for the utility function, this in textbook-like form, and the lower equation is what it looks like in Excel. So this formula is what is in this cell and this cell. The expected utility is just these values times the probabilities. So expected utility is 7 million risk-neutral dollars, numerically the same as the EMV, but that's going to change when we reduce R. Once we have expected utility, we can calculate the certain equivalent. So again, the upper equation is a textbook-like formula, and Excel's formula is this lower one. So this is the formula in this blue cell in Excel. Our answer in the previous problem had PS equal to 50%, so I'll go ahead and change that now. And let's put R down to a much smaller number, say 100 million, and see what that does. The new EMV with 50% chance of success is $2.5 million. And the EU number now is not the same. It's lower because of a more reasonable, risk-averse, risk tolerance coefficient. And here's our certain equivalent. The disparity between these two numbers will increase as R is reduced. For example, if R is $10 million, this has gone negative, and that's perfectly acceptable that we would have a project with a positive EMV, but because of risk aversion, it might have a negative certain equivalent. In this PS type question, the decision maker would assess what P sub S would be the minimum amount, the minimum probability of success before he or she would be willing to approve the project. At that point, CE becomes positive, or EU becomes positive. We can look at either one. So to find the R that gives us a positive CE, or just positive CE, let's go ahead and use the goal seek function in Excel. So I want to set this cell equal to 0 by changing the risk tolerance coefficient. And we find that when R is 10.39 million and all these other parameters are the same, we have break even. Our certain equivalent is just turning positive, as is the expected utility. So this type problem was set up for a PS type question. A certain equivalent type question is done almost identically. We can use the same spreadsheet. So for example, if our decision maker said, I think, given all these parameters, that this is worth, say, $1 million to me, I could set CE to 1 million by changing R. And that's saying that if R is 18.24 million, this risk has a $1 million certain equivalent to this decision maker. Solving for a share type question is a bit more difficult because we would need to add share fractions to the outcome NPVs. We would use Excel Solver. UEP has only two visible functions. It generates a random question based upon user settings. Then UEP processes the answer into the risk tolerance coefficient. Here is the UEP startup screen as UEP first appears in your browser. UEP randomly assigns question type and buy or sell perspective. These buttons are set for share, question type, and buy perspective. The default currency units are K dollars. This is just a label for the NPV, EMV, and CE amounts. This is just a label and you can enter up to 8 characters. What is the maximum amount you would normally risk on any project or venture? Enter this in currency units in the max risk field. This is used to scale questions approximately to fit your situation. Click Next Question button to generate an investment decision. Here's a question UEP generated. I'll zoom in to the text. The investment for your consideration is an economically attractive but large candidate investment. You are acquiring or increasing a share of this project. At the top are NPV outcomes, $167,000 for success and minus $88,000 for failure. We assume that the NPV of failure is the investment amount. $88,000 is more than you would normally risk on any one project. The EMV is $61,000 at PS judged to be 58.6%, so the project is economic. A project like this will add, on average, $61,000 to the company's NPV. The next two decision metrics are supplemental and not required for our expected utility decision policy. However, most companies operate under the belief of a capital budget limit. These criteria are of interest to some decision makers. Discounted return on investment, 0.70, is the ratio of EMV to investment. This means every dollar invested returns an EV 70 cents of NPV beyond the recovery of the investment. And this last metric, assume we could somehow assemble a portfolio of 10 identical yet independent projects like this. The portfolio would have a 93% chance of a positive NPV outcome. If UEP had a risk net cash flow projection, I would add an internal rate of return calculation to these supplemental metrics. After careful consideration, suppose that you believe a 60% share of this project would be most appropriate. Enter 0.6 in the answer box, press Enter or click the green Go button, and UEP quickly calculates and returns the inferred R value. If you are well calibrated and consistent, we would now have your risk policy. However, most people need practice and feedback to calibrate their intuition in making risk versus value trade-offs. With practice, you should become better able to answer risk questions in ways that produce consistent R values. There's more. Below the text question is more information that may be helpful to your decision. Some people prefer a graphic. The typical maximum investment was left at the default $50,000, so the $87,000 may be too much to risk on a single project. The key metric, EMV, is indicated at the chance node. Below the node entry line are those two supplemental metrics that may be of interest to some decision makers, especially if capital constrained. Discounted return on investment, and the probability of success with a portfolio of 10 like projects. And the share type question, what fraction is optimal? Below the node graphic is a table that also might help with the decision. The table shows the reward share, risk exposure, and EMV for different share fractions. Here the 60% answer is highlighted. Let's summarize. Most everyone cares about risk at some level. If you are a conservative decision maker, then a quantified risk policy will be helpful for clarity and consistency. Judging risk versus value trade-offs is difficult with unaided intuition. A quantitative risk policy guides in making logical, consistent trade-offs between value and risk. The exponential utility function shape offers key benefits. UEP will help you determine the risk tolerance coefficient. If this approach to risk policy interests you, try UEP by visiting this website. I would love to hear how this works for you. Here's that URL again to access UEP. There you will find other links to companion videos and white papers. I wish you success through better decision making. Thank you for watching.